Okay, welcome to DLS Spring 2026. I'm excited about the range of speakers this semester. I think you'll see there's a number of different flavors of hydrology, hydrogeophysics, chemistry, morphology, and then a mix of speakers recommended by you all. And before Lauren introduces the GEOSLAM students today, I just wanted to say if you are registered for DLS, please hang back after the last talk so that Isak and I can talk about expectations. But otherwise, Lauren.
Okay. Great. Thanks everybody for coming. Always a well-anticipated and attended event here, the GeoSlam, which is modeled after a poetry slam. And of course, many of you heard the faculty slam. I think that was last semester we did that. So we actually are doing this year in two parts. There are 14 new graduate students in our program that we're welcoming, and they're going to tell us a lot more about themselves and their research. So we have, let's see, I think we have 6 presentations lined up today, and then 8 next week due to some sicknesses and shifts. So really glad everyone's here, and I know these students have done a lot of work. I'm evil and make them go through this twice in reviews. It's a bit tedious for everyone, but it's always really awesome to see them sort of improve, and I think you're going to see some really great, talent and intelligence and sort of really creative ideas here in this department. So without further ado, I'm going to go ahead and introduce each student. Each student has about 7 minutes. We have a little bit of leeway with that, with a sickness, so that's good. If we won't have questions between each presentation, however, at the end, when we're finished, the speakers will hang around, and so if you want to ask them a question or tell them how awesome they did, you can come up to that afterwards. Okay? All right. So I'm going to invite up our first speaker, who is Isaac Bauer, and he's going to give us a first look into international monitoring systems, seismic data for studying the deep earth. Go ahead,
First, just a little bit about myself. I'm sort of from all over, but I grew up mostly in North Carolina. I got my Bachelor of Science at UNC Chapel Hill in geoscience, but my coursework and research focused much more heavily on geophysics. I did my undergrad thesis on numerical modeling and wave propagation of infrasound signals. And then after I graduated, I went on to spend the summer interning at Oak Ridge National Laboratory, where I continued working on wave propagation and infrasound. And at Oak Ridge, I was in the Nuclear Nonproliferation Division, and I got really interested in some of the forensic applications of seismology, so like seismic source discrimination for differentiating earthquakes and nuclear tests. But at UNC, I became very interested in large-scale global problems in geophysics and seismology, which got me interested in studying the deep earth, and that's what brought me to Utah, where I'm working with Mike, specifically studying the structure of the lower mantle and the core mantle boundary. So first, I'd like to start off just by explaining my data. I'm using International Monitoring System seismic data. The IMS is a network of seismometers, infrasound sensors, and radionuclide stations that's used by the Continental Test Ban Treaty Organization to ensure compliance with international nuclear law, basically to detect and enforce rules around nuclear testing. And over the past couple decades, the IMS has provided the geophysics community with quite a bit of seismic data, particularly from these arrays, which are in pink on the map. And arrays are very useful for studying the deep earth, which is why I'm using them. And specifically, I'm studying ultra-low velocity zones. These are patches of low velocity material that sit right on top of the core mantle boundary. And their origin and composition is still somewhat debated, but there's pretty strong evidence that they could be derived from subducted slabs. They've also been correlated to hotspot regions, and they could be connected to larger processes in planetary formation and differentiation. Very interesting and relevant to study. And to study them, I'm using the SCP phase. This is a type of seismic phase that's really useful for studying UOVZ. It's basically a type of seismic wave that originates from a very deep earthquake, usually below 100 kilometers, and then it travels down through the mantle as an S wave. It enters the UOVZ, reflects off of the core mantle boundary, and converts to a P wave, and then it travels back to the surface where it's recorded by a seismometer. However, because of variations in the shape, density, thickness, geometry of the UOVZ, it can also produce these precursors and postcursors, which arrive before and after the main SCP phase, right there. And these are very useful for studying UOVZ because they're sensitive to the structure. So a lot of the IMS data set is pretty new data and hasn't been looked at thoroughly. So my goal is to look through the IMS data, try and identify the SCP phase and these precursors and postcursors to locate UOVZ on a global scale and then examine their physical properties. And I've decided to show you one earthquake that was recorded by a Mongolian array. I've chosen this array because there have been very few papers that have looked at it, and none of them are on UOVZ. So this was an earthquake that was recorded in 2008. It was magnitude 6.2 and was 132 kilometers deep, which is in the upper mantle. And this is what the array detected. So each of these lines is a different seismometer within the array. And just based on ray tracing and sort of an eyeball estimate, I can say pretty confidently that this is the P wave arrival, the S wave arrival, and the SCP wave arrival. And zooming in a bit to the SCP phase, you can see there's a pretty clear arrival. And it also looks like there could possibly be a couple precursors and maybe a postcursor right there. So this is all very preliminary, but because we can do this, it's likely that the Mongolian array is sensitive enough to be able to be used for this type of analysis, which is really exciting. That brings me to my future goals. Looking ahead, I plan to use more analysis techniques, which are really useful for increasing the signal-to-noise ratio, and that makes it easier to pull out the precursors and postcursors. Then also one of my longer-term goals is to compare these results with data, synthetic data from numerical models. The idea is if you run a model with certain predefined UOVZ conditions, for example, 20 kilometers thick, you can take the resulting model, compare it to the data, calculate the error, make a small adjustment in the model, and then iterate until you have a model that produces a result with the least amount of error. And that's what this figure is showing. This is from a paper by Surya Pichai in our department, and also my advisor Mike. And it's showing basically this exact same process, just with a UOVZ in the Pacific Ocean near New Caledonia. So this is the kind of result that I would love to get from, for example, the Mongolian array. Each of these panes represents a different physical property of the UOVZ, so like thickness, S-wave velocity, cruising velocity, density. And hopefully this kind of process could be used to give more evidence to UOVZ's possible origins in subduction or possibly its composition, such as partial melts or iron-rich material. And lastly, just some of my other hobbies. I'm obviously obsessed with anything sci-fi or horror, so if anyone has any book or movie recommendations, I'll happily take them. Here's some of my favorites. I'm also a black belt in karate, and I also play the classical violin, so there's some things that I do for fun in my free time. Thank you.
Hey, thanks, Isaac. Our next speaker is Brian Sharp, and he's going to tell us about his project in seismic imaging. I did, I made all the content.
Thank you very much.
Yep, and I
Appreciate
checked it before.
Great. What a great professor. All right. My name is Brian Sharp. I'm a new PhD student working with Fanchi and Jamie. I'm doing seismic imaging. That's a picture of me and my wife, my son who's 2, and then my other son who's now almost 1. When I'm not doing research, I'm usually hanging out with them, going to parks, Natural History Museum, changing diapers, all the fun stuff you get to do. A little bit about my road to how I got to the U. I grew up mostly on Oahu, Hawaii. Like surfing, being outside, and it's pretty hard not to, fall in love with geology when you grow up on an active hotspot like Hawaii. And so I did. And I came to Utah, actually, went to BYU to get my undergraduate degree. and geology. And that's where I was introduced to natural hazards. I didn't quite do earthquake stuff, but I did do stuff in Indonesia looking at tsunami deposits, using some drone imagery. Got to go to Indonesia, which was really fun. But when I finished my bachelor's degree, I went to San Diego State, where I got my master's degree in geophysics. And it was there I was looking at earthquake simulations in California. And I really liked my time there, being in San Diego. But I honestly felt like I got too deep in the weeds. I missed geology a little bit. I missed being outside and not staring at a black screen all day. So I went to Utah because I found out Fanchi and Jane were accepting a PhD student doing seismic imaging, which to me is really exciting because it's like you're using geophysical methods, but ultimately what you're looking at is what's the subsurface, what is the geology doing beneath you. So it was a great fit, and I'm happy to be here. So hopefully, if my pattern of beach, mountain, continues, I'll be on the beach pretty soon. Here is a little bit of introduction of what my project entails. If I can play this, there we go. So my project is based in Northern California. Northern California has a lot of faults, a lot of earthquakes. And something really cool that we can do is we can do earthquake simulations. So here's on this left panel, we have a simulation of a magnitude 7 earthquake on the Hayward Fault. This is San Francisco for reference. And you can see, how the ground motion propagates. It's very complicated. And from this ground motion, we can then estimate the building damage from that future earthquake. So it's really cool. We can save lives. The issue is that this simulation, and hence the estimations, are only as accurate as the input parameters into these simulations. And one of the very important parameters that we use is the velocity structure, how fast the waves move beneath the surface. And often in the upper couple kilometers, it's pretty inaccurate and low resolution. So that's kind of where we want to come in and help. So my study area is in the Livermore Basin. So here's San Francisco. The Livermore Basin is this strangely shaped triangle basin right here. And what we've done, or what we're doing, is we have deployed almost 200 seismometers, that's what those little pins are right there, all across the Livermore Basin. And what a seismometer is it's one of these little things, and it has a battery life, this one, at least around a month, and so we'll leave them out for a month, and after a month we'll go and collect them, and we replace them. So we're actually almost done collecting our second month of data in about a week. But these will record ambient noise, so really small earthquakes and just noise from Earth, and also real earthquakes as well. And with this data, we can understand what the subsurface looks like. But I wanted to pass this around. You guys can take a look at it. If it starts blinking, it might explode, so be careful. But to get a little bit in the technical part of what we're doing with this data, is we're going to do a joint inversion to look what the subsurface will look like. So there's 3 things that we need for this joint inversion. The first one is called the H/V ratio. And the way we get the H/V ratio is we look at the ambient noise and we extract Rayleigh waves, which is just a type of seismic wave. And we can look at the particle motion of these Rayleigh waves. And from the shape of the particle motion, we can understand what it is beneath it. So if you have a more vertically elongated particle motion, you know that it's probably more of a hard rock site. And if you have more, horizontally elongated, it's probably more of a basin. Another thing that we look at is the phase velocity, which is just how fast these different seismic phases move from one point to another at different periods. And then the third parameter or input that we need is receiver functions. Simply put, as far as my understanding is now in my second semester, is that you have a real earthquake that'll happen, a detectable earthquake I should say, and as we know, earthquakes create P waves and S waves, but as these P waves will come, sometimes they'll hit a really sharp velocity contrast, and when you have this really sharp velocity contrast, some of these P waves will convert to S waves, and you can measure the delay in arrival to our station right here, from the P wave arrival and the converted S wave, and that can tell you a lot about this velocity contrast. So that's the technical part of what we're doing with this data collected by these seismometers in Livermore Basin. what it's going to look like as an end example here, I'll show you some results from a past student of Fenji Gabby. This is also an array that they did something very similar in Northern California. And on the top, this is the end result, essentially. It's a cross-section. Who doesn't love a good cross-section, right? We got these different stations on vertical columns, and we have depth here, and then the colors represent the velocity. And what you can sort of take away is you can see the shape of the basin kind of dips down and goes back up, as well as the velocity we can find out, but we can see what the basin looks like. And we can compare that to active source, which is different than ambient noise, which is what we're doing. And this active source tomography is much more expensive to do, but you can see that the results, are somewhat similar in this survey as to what Gabby got in her results. So this is what we want to do. We want to be able to get a cross-section like this, understand what the velocity structure looks like, what the basin looks like in the Livermore Basin, to hopefully improve the earthquake simulations, and ultimately to save lives. So if you have any questions, I'll be around in the back, but thank you very much.
Thanks, Barton. Okay, our next speaker is Madison, or Maddie Ward, and she's going to tell us about some of her upcoming work.
All right, good afternoon. My name is Maddie. Right off the bat, I'll tell you I graduated from Clemson University back in 2021 with my bachelor's in geology. Took a few years off and then decided I wanted to go back to school, so I decided to go to the University of Aberdeen over in Scotland, where I was able to finish my master's degree in geophysics just last fall, which then led me to want to continue my studies and research. So now I'm here at the U as a first-year geophysics PhD student. I am interested in seismology, specifically looking at some of the active volcanoes out in Hawaii. So before I jump straight into my research, as we all know, research is a collaborative effort, so there's a few people and groups I wanted to acknowledge. My supervisors, Jamie Farrell and Fanchi Lin, both researchers here within the department. The Swiss Federal Institute of Technology over in Zurich, these are our main collaborators. They're providing about a third of the data that I'll be processing. And then of course over in Hawaii we have the USGS. They own and operate one of the permanent networks out there. And so that's another third of the data that I'm kind of sifting through right now. The University of Hawaii has graciously let us borrow some of their grad students to help us with our field campaign and deploying and retrieving seismometers. And then, of course, considering the Native Hawaiian consultation, the permit process goes through the Park Service, and they actually consider the Native input on that, as well as helping us conduct an archaeological survey prior to boots on the ground, just making sure that we stay respectful and that we're not disturbing any historical or cultural sites. So why do we care about all of this stuff? So for those of you who don't keep up with volcanic activity, back in 2018 there were some pretty big eruptions, and it caught the interest of our research group. The reason that it was so interesting is that some of the first lava exposed in the 2018 eruption actually consisted of the same chemical composition as some lava from the previous eruption in the 1950s. And so that was telling us that the magma is being stored underground and that it can actually also be remobilized. So that's why we care about this. There's a whole magmatic plumbing system, and while Hawaii is home to some of the most active volcanoes in the world, the subsurface is still poorly constrained in that area. And so of course talking about volcanoes, you can't really talk about volcanoes without talking about hazards. And so while yes, the summit eruptions can be dangerous, the rift zones are actually where the more dangerous eruptions occur. These rift zones are areas of the volcano that are more prone to fissures and cracks, and these are primary conduits for lava flows. And so these are usually around the flanks of the volcano. And these are the more dangerous eruptions. And the rift zones will kind of play a part in the instrument placement, which I'll talk about in a minute. And then of course, how this varies over time. We don't want to know what the subsurface looks like below our feet for one single day. We want to know how this evolves over the course of weeks to months to even years. So I'll be looking at data from both 2024 and 2025. So just a little bit about the data collection. Briarton passed around the seismometer. It's floating around somewhere in the crowd. These are 3 component nodes. That's just because there's 3 individual geophones oriented in different directions within these nodes. So the north, south, east, west, and vertical components. That's just giving us a 3-dimensional comprehensive overview of any seismic waves that we're recording. Now the data that we're actually recording is not an impulsive source, so we're not using a hammer and plate survey, we're not using dynamite, we're not using a vibro-sized truck. We're simply just allowing the nodes to record natural seismicity. So that can be active sources like an earthquake, or it can just be passive ambient noise, the natural seismic hum that the earth produces every single day. Either way, this is continuous data collection. We let these nodes sit out there, collect 24/7 for about a month or two at a time. And this is the whole point. But where we're putting these nodes, you can see on this map, this is just for the 2024 deployment. I do not have a 2025 map as of right now. So there's a couple different things to take away from this map. So first off is the green triangles. That's the permanent network that I mentioned previously, owned by the USGS. Now the permanent network is continuously collecting 365. It was established in the 1950s, and so it is a very robust and reliable data source that we are using. Of course, as you can see, these green triangles are kind of spaced a little bit farther apart, and so while this is a great foundational understanding of what's happening, it's a little too far for us to get details of what we want to see. And so that's where temporary arrays come in. We have two temporary arrays on this map. The blue one, here. The blue arrays are owned by or deployed by the University of Utah. These are linear arrays, and as you can see, they're kind of in straight lines. These are actually targeting the rift zones themselves, and so this is giving us a more detailed resolution of the subsurface surrounding those rift zones. And like I said, those are a little bit more dangerous, so we want to get a better idea of what's happening there. The other array is this purple array here. It's a 2D array, so it's not in a single line, it's more two-dimensional. That's more spatially conscious, and so this is actually focusing on the Kilauea region. And so both of these temporary arrays, as you can see, the triangles are a little bit closer together. That's just going to give us a finer resolution of the subsurface. Now, so as you can see, this is just 2024. There's about 3 separate data sets within this. And so while I don't have a map for 2025, it's the same idea. I'm still using the permanent network, the green triangles, to get a good baseline of what's happening. But we also have temporary arrays that we've collected as well. Those are also focusing on Kilauea, but also Mauna Loa as well. So I'm currently waiting for those to get processed and get back to me, but this is all the same premise, just 2 different years. And then just trying to wrap it up and kind of tie it all back together. So again, there's 2 different data sets over about a month or so, 2024 and 2025. I want understanding what's happening in these data sets individually. The whole driving force of this research is to understand where the magma is being stored and how it's being remobilized and transported during eruptions, prior to eruptions, and in between. And then, of course, studying how this changes over time. Again, we want to understand how this is changing on day-to-week time scales, but then also over the course of months to years. Understanding how this evolves and how the subsurface behaves, and understanding the magmatic plumbing system of these volcanoes can also help us assess risks as well. And then, of course, overall, what I'm hoping you just take away from this is that at the end of the day, we're just trying to get a better understanding of the subsurface surrounding some of the most active volcanoes in the world. So, thank you.
Thanks, Maddie. Okay, our next speaker is Elani Bonilla, and she'll tell us about evaluating nickel and cobalt mobility during hydration and carbonation of prototypes.
Yeah, so thank you for your introduction. My name is Elani. I'm a first-year PhD student working with Juan Carlos. So getting into a little bit about me, I got my undergrad education at the University of Southern California. I got my BS in geological sciences and a minor in marine biology. I've always wanted to be a scientist. After I was 3 years old and I saw this movie for the first time. And I always wanted to work at a museum after I saw this character on TV around that same age. And what's cool is I actually got to work at the Natural History Museum in LA. I worked at the Marine Biodiversity Center where I digitized marine invertebrate specimens from different collection rooms. And I worked at the Mineral Sciences Lab where I identified different sources of black carbon from sediments that be trapped in bird feathers using Raman spectroscopy. I initially wanted to do something bio-related, like be a paleontologist and study sharks. I'm not doing that anymore. My interest shifted towards geochemistry after my undergraduate research project, where I identified what minerals hosted nitrogen in serpentinites, because that can have implications for how nitrogen is cycled during subduction. It pretty much reframed my understanding of chemistry for me. That was initially a very challenging subject, and it helped me appreciate how these small-scale processes in chemistry and physics can tell us about these large-scale events over the course of Earth's history. And I thought, what better place to study that than here at the U? So getting into my project, nickel and cobalt and why we care, they're both critical minerals, and demand for them is expected to increase up to 350% by 2050, and that's a lot. So that might lead mining companies to look for new sources for these elements to meet that demand. And in order to better predict these sources, we need to understand elements mobility, which just refers to how elements behave during fluid-rock interactions. Traditionally, nickel is considered to be an immobile element, meaning prefers to stay in the rock. And since cobalt is geochemically similar to nickel and they're often mined from the same ores, it's also considered to be immobile. However, there has been recent studies to expose them as being able to be mobilized, and particularly in peritite to listenite transitions. So these rocks aren't known to have a lot of nickel. Peritites typically have less than 0.3% weight percent. So while there is evidence to suggest that they can be mobilized, the extent and mechanisms of these elements' mobility and these transitions remain largely unconstrained, and that's what my project seeks to address for my PhD. So when I say peritite to listenite transitions, I mean an alteration sequence. So peritites are ultramafic rocks, and their minerals can undergo different alteration reactions depending on the nature of the fluid they interact with. So hydrous fluids leads to peritites altering to serpentinites. Carbon dioxide-rich fluids leads to serpentinites altering to soapstones and lispenites. Soapstones are partially carbonated and lispenites are completely carbonated. You can find these transitions in different ophiolite complexes around the world. My samples are specifically from the Oman ophiolite from the drilling project called BT1B, and my samples range from partially serpentinized to completely carbonated peritites. So this project has three main objectives. The first one is what I'm currently working on, and that's mapping nickel and cobalt distributions and understanding the textural relationships using petrography and SEM. So pretty much understanding what minerals are in each sample and which ones are nickel and cobalt bearing phases. The next step is to assess the nickel and cobalt abundances at the mineral scale using the electron microprobe. So once I've identified the nickel and cobalt bearing phases, the next step would be to quantify how much is in each sample. And the last objective is to establish nickel isotope fractionation by measuring the delta 60 nickel isotope ratio using ICP-MS. I won't be looking at cobalt because it only has one stable isotope, but this is pretty much a ratio of nickel 60 over nickel 58. So isotopes can be used as tracers for element mobility because there have been previous studies that show that heavier isotopes, nickel isotopes, prefer to leave with the fluids. So depending on what the ratios are in my samples, they can reveal the extent of the fluid-rock interactions they've undergone. The first two objectives will pretty much make up my first project. The third objective will make up my second project, and the third is to be determined. So I do have some preliminary data from samples that are from the same core as my samples. So the left is molar magnesium over silica ratio plotted against carbon dioxide. All my samples are ultramafic, so they're going to have similar magnesium and silica ratios. What changes is the amount of water and carbon dioxide in each sample. So serpentinites are the ones in green and lispenites are the dots in blue. So carbon dioxide increases as these samples undergo progressive alteration from peritites to lispenites. The plot on the right is carbon dioxide concentration plotted against nickel concentration. There's not one clear trend, but it's evident that lispenites can have either more, less, or similar nickel values as serpentinites. And we can further subdivide them into maybe a group here, a group there, and a group there. What this tells us is that the chemical composition of these lispenites vary despite them all being the same lithology, and that could have implications for how nickel is distributed in each sample. Based on some literature reviews that I've been doing, I expect to see nickel and cobalt mobilized into phyllosilicate minerals during the serpentinization process, with their mobility decreasing as peritites go from partially serpentinized to completely serpentinized. I also expect these elements to be retained within those phyllosilicates as carbonation progresses. And also, just some personal goals for myself, I'm not coming to you as an isotope geochemist. I have some background in isotopes and mostly metamorphic petrology and bio. So this is an opportunity for me to grow as a scientist and become more well-rounded. I also hope to use this research for my project as a Williamson Fellow. I hope to incorporate what I teach my kids at Clayton Middle School. And yeah, that's it.
Thanks, Ilani. Okay, our next speaker is Johan Ren, and he'll tell us about tracing the hidden stories of Earth's interior. Go ahead.
everyone. My name is Yuhan and I'm a first year PhD student here. Locally politics marks. And first about myself, this is my education background. Very simple. I graduated from the Chinese University of Geophysics, got my bachelor degree, and then I come here for the 4-year study. And this is my personal hobbies, occupation. These three are really my daily life, and just sometimes I will feel like, okay, I'm kind of dying at my bed, so I will do some outdoor activities and to explore some new things. And there's some pictures, go to the beach, or some park, or go to another place, and do some geological sightings, and or do some strange things. This is the wooden door, I think. And this is, when it comes to research interest, I'm very interested in the application of the asphalt geochemistry and phospho chemistry, and the volatile cycling, especially the deep part in deep earth, and the metal dynamics, like the convection between the metal and the metal. So if you guys have something more discussion with me, I'm very happy to do this. And of course, other things and other files are very common, but but I know nothing about them. And this is the research area. My main research area is the Basin and British Province, the western US. And the left figure is my sample positions, and the right figure is the tectonic maps. This province is one of the most tectonic active regions, and it means there are many extension and faulting, so there will be lots of magma, especially basalt eruption. And they come from 3 different sources, like the sky influence and hotspot drive, and the original interface basalts. So it is an ideal place to research and understand my research interests. And the significance, this is a figure of the critical minerals. As we can see, there are plenty of critical minerals lies in the central province. So understanding the precise and the mechanism of the magma eruption is good help to understand the formation of critical minerals. And this will also offer a new view to the material cycles and the concept formation, and especially the metal genetic. And my topics really formed by 3 parts. And the first part is to use the first row transition elements to understand this precise. Then this is some live work, first some live work, and then some analyzed work. As this slide will tell which materials melted, and to understand the origin of the metal sources. And the second part, I will introduce the isotopes in this study. And firstly, the iron and zinc isotope, because iron is very effective isotope to trace the metal mechanism, and zinc is the tracer for the subduction materials. And maybe I will introduce more isotopes here, but now there are these 2. So this will get further understanding of the magma processes down the metal. And the third part is to link them together to get a systematically picture of the magma, of how the continental basalts come from in the Basin and British Province, and try to understand the metal processes in this huge area to get the systematic conclusion. And this is a very short plan, a very rough draft. Because as you can see, there are only 3 years, and I think I can't graduate within only 3 years. This is not all my work to do, but I'm happy to have a work plan, so it will make me better to work. Okay, that's all. Thank you.
Okay, thanks, Iman. Last but not least, we're going to going to tell us about mechanisms of rare earth element enrichment in Cretaceous coal-bearing sedimentary strata.
Thank you. I am Logan Asher-Snicki. Just a little bit about me as a person. I got my AS degree at Salt Lake Community College. I got my BS degree here at the University of Utah in the G&G department at the end of 2023. Between my 2 degrees, I worked for McKay Mineral Exploration as an exploration field geologist. When I'm not doing geology things for work in school, I like to do geology things for fun. And I also really like nerdy tabletop fantasy things. I was obsessed with Magic the Gathering years before I cared about rocks. Okay, a little bit of background. What are rare earth elements? Rare earth elements are part of the critical minerals suite. You guys get it, critical minerals are critical. Rare earth elements specifically are scandium, yttrium, and the lanthanoid series. So rare earth elements specifically, why do we care about them? Because we use them in stuff. For example, iPhones, medical equipment, rechargeable batteries, computer hard drives, wind turbines, insulated glass, common household lighting, and electric cars. Please raise your hand if you care about any of these in any capacity. So yeah. Since these are used in so many things, there is a lot of demand for these, which we've kind of already touched on in this session. This graph shows that demand for rare earths specifically has essentially doubled within the last decade and is expected to continue to increase significantly. Over the course of the 2000s, China, the red bar here, has largely dominated the production of rare earth elements. So over the course of the 2000s, the US and the rest of the world have started to make their own domestic pushes to locate their own reserves of rare earth elements. One of the reserves that we have here in the US is coal. So like if you've ever driven down to Helper Canyon and you've seen those black horizontal seams in the sandstone sequences, that's what we're talking about. Just last year, a mine opened up in Wyoming where they're actually mining rare earths out of coal-bearing strata. And over the last few years, the DOE has funded a bunch of research here at the U, looking at the rare earths that we have in the coal-bearing stratas of Utah and Colorado. So there's been a lot of work done here over the last few years, and I want to give a quick shout out to the squad. Laura Wilcox, Peyton Fawcett, and Haley Coe have been awesome colleagues. They really helped me understand what the heck is going on with the research and also just progress as a student. And through their own research efforts, they have built an awesome foundation for me to start building my project off of. I also want to give a huge thank you to Dr. Bergenheyer for bringing me back to the team as a graduate student. A lot of the work we've done has been in the way of geochemical analysis of rock samples and core samples. There's almost 2,000 data points that go into this graph right here. Essentially, all that this is showing us is that we have some rocks that are enriched. Most of them are not. When we say enrichment, we just mean 200 parts per million total rare earths, so we just sum up all our concentrations. If that is 200 or more, that sample is considered enriched. The enriched samples tend to not be the coal rocks themselves, but the mudstones and sandstones that are in these coal-bearing stratigraphic packages. We've also started to resolve an inverse relationship between rare earth concentrations and the quality of the coal that is present there. What we would like to know more about is how did they get there? We have a good idea that they probably came from some igneous hinterland and then throughout the Mesozoic made their way down to the delta and shoreface deposits that are on the western margin of the Cretaceous interior seaway that sliced North America in half during this period of geologic history. What we're less sure about is how much of their transportation was the result of classic surface plastic processes, weathering, erosion, wind, water, sediments moving over the surface, and how much of their migration was the result of a diagenetic influence that occurred post-burial. Now these are in sedimentary rocks, which means that they have sedimentary facies. Sedimentary facies just being characteristics about the rock that represent the environment and conditions that those sediments were deposited under. When you do this for a series of strata and build one of these facies models, what you're essentially doing is you're telling a story. The story is what environments and processes occurred in the place that you're standing over the amount of time that is represented in your outcrop. So my research question is this. What happens if we build rare earth element concentrations into one of these facies models? This is just me grabbing a bunch of bars and stealing a graph from Haley and throwing it all together to look at what this could kind of look like. Hopefully whatever I produce looks way cooler than that. If we do this, can we see what part of the story enrichment occurred? So here's how we're going to go about testing this idea. So we're gonna sample up more sections, measure more sections, and build more facies models. The number one priority in doing all of this is obviously to be safe, because these rocks can be pretty sketchy. As we make these facies models, we're going to take our samples up the section, we're going to document where these samples belong within the facies model, and then bring them back here to the U for geochemical analysis. This is primarily going to be done with portable X-ray fluorescence, PXRF, which is able to detect a subset of rare earth elements. We're also going to set aside a subset of samples for ICP-MS analysis, which is more accurate, so that'll help us qualify our PXRF data set, and maybe also give us a peek into some elements that are kind of beyond the XRF's detection limits. So going forward, right now we've got our eye on this outcrop out by Ivy Creek. It's just north of I-70. I'm sorry I didn't throw a map in there for you guys. And if you see from that vertical red bar right there, that's our enrichment threshold of 200 parts per million. So this outcrop is pretty fat with rare earth elements, and we really like to see that. So this is our current area of interest. We're going to go back there. We're going to make more sections. We're going to make more detailed facies models. These samples right here were actually collected by me and Peyton in 2023. And I think this particular outcrop was never actually in the plan. We were just kind of out there and we're like, that looks cool, let's go grab some rocks. And then they came back really hot, so we're kind of looking at that area again. Ultimately, the goal is to document more samples in geochemistry and then also get a really, really good sense what is going on specifically right there in those sections and outcrops that we are building this sample from. By combining the sedimentology and the geochemistry, we hope to be able to establish relationships between the ancient processes that were happening at the time and the enrichment that we are seeing today. The ultimate goal of establishing those relationships is to try and determine any rare earth element mechanisms, any enrichment mechanisms that is resulting in the rare earths that we are finding. A big part of this will be generating virtual outcrops. These are really, really nice and handy because they allow you to visit your field area right there from your desk and not have to email Will about vehicle availability. Another really awesome thing about them is that you can annotate them and plot whatever you want on them, almost like you were a giant 2,000-foot person with a paintbrush just painting on the cliff. This will hopefully make it really easy to visualize and represent these relationships. And we care about these relationships because we would like to determine the mechanisms of rare earth element enrichment in this strata. If you have any questions, come hang out later.
Hey, thanks, Logan. Okay, that concludes our session. Just want to thanks to all of our speakers for their excellent presentations today, and just wanted to let everyone know that those folks will be here if you have questions. So, thank you.